carbon NMR, there are only 4 key chemical shift ranges that you really need to know. Okay, 5 key ranges, but I'll explain in a second. When you get to spectroscopy land and you analyze your spectra, you have to know your chemical shift ranges without even really thinking about it. In a previous video, I went through the 8 chemical shift ranges for proton NMR. If you'd like a refresher on those chemical shift ranges, you can watch that video linked down below. As we go through the chemical shift ranges, this video isn't really about how carbon NMR works or how to interpret those ranges, but I do have an entire spectroscopy playlist that I'll link to down below. The furthest upfield range runs from about 0 parts per million to about 50 parts per million. The nice thing about these chemical shift ranges is, from a mnemonic standpoint, we can pretty much chop off every 50 parts per million unit as a different range. This range is for the regular boring sp3 hybridized carbons, the alkyl range. As we move through these various ranges, let's use this molecule on the top as our guide. How many of the carbon atoms in this structure do you think will fit in the 0 to 50 range? In this structure, there are 3 sp3 hybridized carbon atoms that would fall into this range. I can already hear what you're saying. There's a 4th sp3 hybridized carbon up there. Why are there not 4 signals in this range? That's a great question. I'll come back to it in a second. These 3 carbon atoms, however, are the ones that will fit in the 0 to 50 regular boring alkyl type carbon range. Where will they be within this range? Well, the further away they are from electronegative elements or electron withdrawing groups, the closer they'll be towards 0, but it's hard to predict exactly where in this range those carbons will fall. The next range runs from 50 parts per million up to about 100 parts per million. These are for carbons that are sp3 hybridized that are attached to heteroatoms. I refer to these as the CZ type carbons. Recall that a heteroatom is an electronegative element like oxygen, nitrogen, fluorine, chlorine, or bromine, and for this molecule there's 1 carbon that would fit into this range. Can you find it? Here is the 1 carbon that would fit into this range. It's the one that wouldn't fit in the 0 to 50 range. And now we can see why. That carbon is directly attached to the oxygen. That makes it a CZ type carbon and would fit in the 0 to 50 range for the heteroatom region. The next range runs from about 100 parts per million up to about 150 parts per million. It's really nice that these break along 50 parts per million intervals. The signals in this region will be for sp2 hybridized carbons doubly bonded to other sp2 hybridized carbons. These will be for vinyl or aryl type carbons. Vinyl carbons are carbons involved in a carbon-carbon double bond in alkene. Aryl carbons are carbons involved in an aromatic ring like benzene. How many of these carbons do you see in this structure? There are 6 of these carbons in this structure. But be careful, that does not mean that there will be 6 signals in this region. What I'd like you to notice is the benzene ring has a plane of symmetry that's running diagonally through the benzene ring. That means that the 2 carbons in the top left are symmetric with the 2 carbons in the bottom right. Those pairs of carbons are equivalent, and so we will not see 6 signals for the benzene ring for this molecule. We would only see 4 signals for the 6 carbons in this ring. One other misconception I'll point out here for this region. We will see a unique signal in this region for every individual carbon atom that's sp2 hybridized bonded to another sp2 hybridized carbon, not every pi bond. Sometimes students will see 2 carbons in this region and assume there must be 2 pi bonds because they think that each signal represents a pi bond. And that's not the case. They represent sets of equivalent carbons, not bonds. So if there were 2 signals in this region, that might tell me that there's 1 pi bond, 1 alkene in the molecule, and each of the carbons of that alkene are a separate signal in this region. The last major region in the carbon NMR is from 150 and above. Any signals with a chemical shift greater than 150 parts per million. These are for sp2 hybridized carbons doubly bonded to an oxygen. Carbonyls. In this molecule up above, there's only 1 carbonyl carbon, so we would only expect 1 signal above 150 parts per million. Let me emphasize one more very important point about these 4 regions. From a mnemonic standpoint, it's very convenient that we can chop them all at clean 50 parts per million intervals. In reality, molecules don't care about our mnemonics. To that end, each of these boundaries is really a fuzzy boundary. What do I mean by that? We've said the signals for alkyl type carbons should fall from 0 to 50, and carbons attached to heteroatoms should be from 50 to 100. But this boundary is fuzzy. It's unusual, but not uncommon, for an alkyl group that is sufficiently electron poor to sneak over past 50 parts per million. If a carbon is surrounded by enough electron withdrawing groups that aren't technically heteroatoms, we might nominally place it in the 0 to 50 range, but the actual chemical shift might be somewhat above 50. But the fuzziest boundary of them all is this boundary here at 150 parts per million. It is very common for some electron-poor benzene carbons to have their signals sneak well past 150 parts per million. Similarly, it's rare, but sometimes carbonyl carbons can be electron-rich and can sneak past 150 parts per million as well. If you see signals right around 150 parts per million, be very careful. Even though the signal may be at 160 parts per million, it might really be a vinyl or aryl carbon that has just snuck past its boundary. It's not uncommon for signals to be slightly out of range, especially at this boundary. If you're not sure about a carbon near this boundary, how are you supposed to know which range it falls into? You can use your other context clues. This isn't a video about IR, but if it's really a carbonyl, that will be really clear in your IR spectrum. If it's really a benzene ring, that will be really clear in your proton NMR spectrum. If you'd like more training on IR and proton NMR, again, I will refer you to the spectroscopy playlist in the description below. The last fifth region that I hinted to earlier tends to settle around 100 parts per million or so. We don't see these types of signals very often, but these are for sp hybridized carbons, alkynes. The carbons of an alkyne, sp hybridized, tend to be around 100 parts per million, maybe a little bit more upfield. That's actually kind of annoying. We already have these chemical shifts accounted for in 2 other ranges. If you see signals in this region, how can you be sure they're not alkyne? You can't, really. But you should have enough other context clues from your other spectra to help you decide if it's an alkyne or not. We really don't see alkynes in spectroscopy land very often, so if you see a signal around here, I wouldn't assume alkynes as my first guess. I can look to the IR though. If there's really a triple bond in the molecule, the IR will let me know. These are the must-know chemical shift ranges for carbon NMR. Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.